we'll discuss one topic on computational fluid dynamics. The topic name is momentum equation derivation. Myself, I am P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. Now, momentum equation, as as the continuity equation is governed by the law of conservation of mass. The momentum equation is also governed by some physical principle, and the principle is the Newton's second law. So this is the of motion. This is the physical principle based on which we derive the momentum equation. Now, what this Newton's second law of motion states? It states that the sum of forces which are acting on the fluid element. So this is the vectorial sum. Okay, the vectorial sum of the forces acting on a fluid element is equal to the product of mass and acceleration of the element. So this is the you have three directions: x-axis, y-axis, and z-axis. So if I consider x direction, so this force, momentum, these are all vectorial things. So we can consider one component, and similarly we can draw the relation for the other two components. So the component which we are going to do is x component. Now what is sigma fx? The sum of the vectorial sum of all the forces acting on the fluid element in x direction is equal to mass into acceleration. Now what is this ax? Ax is acceleration in x direction, the component of acceleration in x direction, and this ax is equal to du by dt. So this is a substantial derivative du by dt, or total derivative du by dt. Now there are two types of forces that the fluid element which is moving in space, say suppose this is a fluid element and it is moving in space, and this fluid element experiences two types of forces. What are the two types of forces? One is body forces, the other one is surface forces. Now what all forces come under the body forces? Body forces are generally they are proportional to mass. The gravity force, the centrifugal force, the Coriolis force, the electromagnetic force, all these forces are body forces and they are proportional to the mass of the fluid element. Now what are the surface forces? Now the moving fluid element is having surfaces. Say suppose it is a cube, it is having some 6 surfaces. Now these surfaces are experiencing some forces, and these forces are called the surface forces, and these surface forces will try to deform the fluid element in different directions. And the surface forces include the normal stresses, the tangential stresses, okay, and the pressure is also there. Pressure also acts. Now the normal stresses, generally they are very negligible. Only when the case, if you take the case of a shock wave, during such cases where the velocity gradient is very high in the normal direction, there only the normal stresses are counted into the the calculation. Otherwise the normal stresses they are neglected. Okay, so the generally tangential stresses and pressure forces only will be considered for all the general cases of fluid flow. Now this as I said, we have normal stresses sigma xx, sigma yy, sigma zz, and the tangential stresses xy, yz, and zx, tau. Now these normal stresses, they act perpendicular to the face. So suppose this is the face the normal stresses act perpendicular to the face, okay, and the tangential stresses they act parallel to the face, okay. So this is the way they act. The pressure acts normal to the face or normal to the surface. The normal stresses act normal to the surface, and the shear stresses, these tangential stresses are also called shear stresses, and these shear stresses are because of the viscosity of the fluid element, of the fluid. Now these stresses act parallel to the surface. Now the local deformation, okay, and velocity gradient, two terms are there, okay. Now these stresses are the function of the local rate of deformation, okay, and they are expressed in terms of the velocity gradient, okay. It should be very clear now. They are function of these tangential stresses are function of the strain rate or deformation rate, but they are expressed in terms of velocity gradient, okay, that we will see. Now say suppose this is the fluid element, the same fluid element I am taking, and the axis along which the force is acting. So we are taking only x component derivation here. So here this figure you can see all the stresses, okay, and this figure you see the pressure force, how the stresses are acting and how the pressure forces are acting, we can see here. Now if delta x, delta y, delta z, okay, delta x, delta y, delta z is the dimensions. Say suppose this is delta z, this is delta y, I can write here, this is delta x. So these are the three dimensions, both are same element. So here it is little clumsy, so I am writing here. So this is what is this? This is delta y, and this is delta z. Now if I want to find the volume of this element, it is the product of these three dimensions, delta x, delta y, delta z. Now if I want the mass, mass is nothing but the product of density into volume, that is equal to rho into delta x into delta y into delta z. Now the rate of increase of momentum, x momentum, okay, the rate of increase of momentum, the rate of change of momentum. So what is the meaning of rate of change of momentum? It is equal to mass into acceleration. This we have seen in the last slide, first slide, previous slide. The mass is rho into delta x into delta y into delta z, and ax is equal to du by dt. So the product gives the rate of change of momentum, okay. So this is the first term, the left hand side of the equation, right hand side of the equation, the sigma fx is equal to ma. So the right hand side of equation is the rate of change of x momentum, that is given by mass into acceleration. So that we have seen. Now we will see what are the forces that are acting in x direction, okay. Say suppose the left face you are considering. On the left face, what force is acting? This sigma x, that is a stress into area perpendicular to the direction of x, okay. So this is acting in this direction. The area perpendicular to this is delta y into delta z. So that is the force acting in x direction. But here it is acting in the negative direction. So this is the positive x direction and this is a negative x direction. So the positive x direction, the forces acting in the positive x direction, they are considered positive. The forces acting in the negative direction, they are considered as negative. So this can be written as minus sigma xx delta y delta z. This is for normal stress. Now on the right face you have a force. Now what is this force because of? Now this stress, it is not constant. This stress is varying per unit length. Okay, so the change of stress, the change of stress per unit length is equal to dou sigma xx by dou x. Okay, so this is the rate of change of stress. I mean, it is not rate of change, it is a change of stress per unit length. Now which stress we are considering? We are considering the normal stress, and the change of stress per unit length is dou into sigma xx by dou x. Now what is the net change? Net change will be given when I multiply this with the length in x direction. The length in x direction is delta x. So this is the change in the normal stress in x direction. Now this normal stress is acting in the positive x direction, so it is a positive term. So I can write this as sigma xx plus dou sigma xx by dou x into delta x, delta y, delta z. Now this is the force acting on the left face, the force acting on the right face, and this force is because of the normal stresses. So the what is the sum of this? This is negative, this is a negative value, this is positive value, and what you will remain with is dou sigma xx by dou x into delta x, delta y, delta z. So this is the value you are left with when you consider the normal stress. Similarly, we will consider the tangential stress. Okay. Now here you have on the top face and bottom face. You are considering now the top face and bottom face. Now what is this? This is a tau yx. Now how it is designated as tau yx? It is acting in x direction and it is varying in y direction. Okay, it is acting in x direction and it is varying in y direction. So that is the designation. This designation is given like that. It is acting in x direction and varying in y direction. You can designate in another way also. It is acting in x direction and it is acting on a face, okay, which is perpendicular to y direction. Okay, that is also given. So easiest to understand is it is acting in x direction and it is varying and it is changing in y direction. Now when it is changing in y direction, the top, what is the change of stress per unit length? Change of stress per unit length is dou tau yx by dou y, because it is changing in y direction. Now what is the net change? What is the height of the element? The height of the element is this one. This is a delta y. So the net change is dou tau yx by dou y into delta y. Now we'll see what is the force that is causing that is caused by this stress. Now the bottom face, the stress is acting in negative direction. So the negative direction means I will get a negative 1 into what is the area on which it is acting? It is this one. What is this? This is delta x and this is delta z. So it is a delta x, delta z. Now the top face, what is acting on the top face? It is acting in positive x direction. So I can write it as a positive one, tau yx. This is the initial value and there is a change in this. So what is the change? Dou by dou y of tau yx into delta y into delta x delta z. This area is delta x delta z. Now if I simplify this, what I will remain with? I will remain with, this is negative value, this is positive value, will get cancelled off. I will be remained with dou by dou y of tau yx into same delta x delta y delta z. So what I will do, I will write it as a common value. So it is a dou sigma xx by dou x into delta x delta y delta z. So this volume is common, so I am taking it common. Now if I consider the other face, the front face and the back face. So the front face is there, the front face and the back face. So this is the front face and this is the back face. Now on the front face, what is the force that is acting? So the front face, this is positive x direction. The front face, the force is acting is tau, this one, tau zx, and the back face it is tau zx into delta y delta z. So this is changing in the z direction. So it is changing from back to front. So the back side it will be less, the front side it will be more. Now what is the change? What is the change now? The change is equal to tau zx. So what is this stress? It is acting in x direction but changing in z direction. It is changing in z direction. As the z increases, the shear stress also increases. Now what is the net value here? So the change in stress per unit length is dou tau z by dou z into delta z. So this is the change in the stress. Now the back force, the force on the back face is acting in the negative direction. So it will be minus tau zx delta x delta y. Now this force acting on the front face is more than this and it is acting in the positive x direction. So it will be equal to plus tau zx plus dou tau zx by dou z into delta z into delta x delta y. Now here also I have two components. One is this is equal but negative and this is positive. If I eliminate this, what I will remain with? I will remain with zx by dou z, okay, dou tau zx by dou z into delta x delta y delta z I have written as a common value. Now if I consider the pressure forces, so what is happening with the pressure forces? So if you observe here, it is a different thing here, delta z. Now here in this case, the starting values are acting in the negative direction, the ending values are acting in the positive direction. And here the starting value is acting in the positive direction, the ending value acting in the negative direction. Now here the pressure, the change of pressure per unit length is equal to which direction it is acting? It is acting in x direction and normal to the face. So it is dou P by dou X into delta X is the net change. So the initial force is plus P into delta X so this is delta Z delta Y. So this is P into the normal area, that is equal to delta Y delta Z. Now this is acting in the positive direction, so we gave a positive sign. Now this fellow is acting in the negative direction, so I am putting a negative value here. P plus dou P by dou X into delta X into delta Y delta Z. Now if I eliminate the first term, the positive negative term equal terms, what I will be remaining with? Minus dou P by dou X delta yeah. Now this delta X delta Y delta Z I have taken common, so this is the term I'm getting. Okay. Now these are the different forces, surface forces. Now we will see the effect of all these forces. What is happening to the element because of all these forces? This force, what it is doing? It is the sigma xx is pulling in this direction. This force, the sigma xx plus sigma dou sigma by dou x, this is pulling in this direction. So it is trying to pull in different directions. Because of that, the volume will increase. Okay, so it is a linear deformation. So it may result in linear deformation. Similarly, the pressure, what it is doing, it is trying to compress. So the change may be, it is a reduction in the size of the element in x direction. But if I see this tangential force, what it is doing, say suppose this is the element, this tangential force on the top one, it is trying to pull in this direction. Okay, and the negative fellow, the bottom fellow, it is trying to pull in this direction. So we'll get a angular deformation. So these shear stresses are causing angular deformation. The normal stress and pressure, they are causing the linear deformation. So this is one important point we should remember. Now coming to the derivation, we are remained with, we have the mass into acceleration momentum, and we have these three values. This is the stresses due to normal forces, and this is the stresses due to the tangential forces, and this is the stress due to the this is the forces due to normal stresses. This is the force due to tangential stress in y direction, the force due to the tangential stress varying in the z direction tau z, and this is the force due to the pressure. And I will also have the body force. Now what is this body force? If I consider a small element, say suppose this is a weight, if I am considering a weight in z direction, it will be there. Similarly, there can be a centrifugal force in x direction, y direction, z direction. So all that we are generalizing and considering a body force F. Now it is having three components, and the three components are Fx, Fy and Fz. So the body force acting in x direction, the body force acting in the y direction, the body force acting in the z direction. So we are concentrating here on x direction. So this is we are taking Fx. Now what is this F? It is as I said, it is proportionate to the mass of the element. Okay. Now density, if we don't consider, we consider only the volume. If this force is force per unit volume, if this body force is force per unit volume, then because the calculation, the weight, centrifugal forces, all those things, they are proportionate to mass. But in the calculations, you will have the density into volume. So we are taking only volume here. Okay. Now the force per unit volume is, the body force per unit volume is F per unit volume. Okay, F is equal to, I'll write once again, F is equal to force per unit volume. Force per unit volume. Now what is the total force? Force into volume, that is written here. Okay. Now, so this is the total body forces in x direction. Now 1, 2, 3, 4, 5. These 5 forces are, the net force is equal to mass into acceleration. So this is the Newton's law. Now if I eliminate, as I said in the previous thing, this is eliminated, this is eliminated, this is eliminated, this is eliminated. If I eliminate all these things, I will remain with this equation. Okay, rho into du by dt plus this. Okay, now we'll see one equation. This is the equation. Okay, I want to relate this term with this. Now what is this? It is a rho into the substantial derivative. So the rho into substantial derivative, if I put, it is equal to rho into dou phi by dou t plus dou u by dou rho into dou phi by dou x, rho v into dou phi by dou y, rho w into dou phi by dou z. So this is these two are equivalent. This is the expansion of substantial derivative. Now what I am doing is I am adding the continuity equation. Okay, from continuity equation we have seen this one. So dou rho by dou t plus dou rho u by dou x plus dou rho v by dou y plus dou w by dou z, like that. This we got the continuity equation, and this is equal to 0. So if I add, this is one term, right hand side, this is left hand side. So left hand side I am adding 0. So there is no change in the value. Okay, I am adding a 0. If I add 0 or subtract 0, I will not have any effect. So I am adding the 0 in the form of the continuity equation. If I add these two, what I will get? This is rho dou phi by dou t, and here phi into dou rho by dou t. If I apply the UV rule, I will get dou rho phi by dou t. Similarly, these two, if I apply the UV rule, I will get this. If I apply UV rule for these two, I will get this term. If I apply UV rule for these two, I will get this. Okay. So this is a using this proof. What I am writing here, I am writing this dou rho into dou u by dou t. What is here? Phi. Phi is an arbitrary function. It can be u, v, w or anything. So I am using a u in place of a phi. If I use u, what I will write here? I will write dou by dou t of rho u, dou by dou x of rho u, dou by dou y of rho u v, dou by dou z of rho u w. Like that I will get. So this is the equation. Okay. Now this equation, this is not a conservative form. Okay, we have to remember this. This is not a conservative form. Why we are doing this exercise is to convert that into a conservative form. So this equation is not conservative form. We have applied that one. We have added the continuity equation here and made it into a conservative form. Now what is this term? This term is equal to rho del dot rho u v bar. Now what is v bar? V bar is nothing but ui plus vj plus wk. And what is del? Del is equal to dou by dou xi plus dou by dou yj plus dou by dou zk. So the product of this, and we don't have del alone, we have dou rho u by dou x, dou rho u by dou y, dou rho u by dou z. That's why rho u is common. You can see here. This is rho u, rho u, rho u, rho u. This is a rho u is a common term. So it is not a vector quantity. It is a scalar quantity. Now the del and v, if I take the dot product, then the equation becomes like this. So this is a conservative form. Conservative form. Now this is in x direction. If I consider in y direction and z direction, what I will do? I will get here, we will see. So here, this is the x direction. In place of x, I will get y. In place of x, I will get y direction. If I am considering the z direction. This is the y direction. This is a z direction. Similarly, x force, y force, z force. Now here, the normal is xx. Here normal is yy. Here normal is zz. Now shear stress, all these things, first one, it is varying in x direction. You keep it common, x, y, z. Okay, it is acting in x direction, acting in y direction, acting in z direction. Now here it is varying in y direction, but acting in x direction, acting in y direction, acting in z direction. Here it is acting in z direction, varying in z direction, sorry, and this is acting in x direction, y direction, z direction. And since it is x direction, we are having x here, differentiation with respect to x, y, y, z, z. And here x direction velocity u, y direction velocity v, and z direction velocity is w. Now if I add the continuity equation on the left hand side, the same equation will be converted like this. So you can see this. This is what we have derived. Similarly, I am writing for u, v and w, y direction and z direction. There is no confusion here. Here u, v, okay, u is there, vu is there, u, w is there. Now in the second equation, if I see v is the common thing. In the third equation, w is the common thing. Okay, in all the 6 terms here, we have 6 terms, and this is acceleration. If you remember, this is a local acceleration. This is a local acceleration at a particular point, and this is the acceleration due to change in point, change in the distance. Okay, now this is a local acceleration, convective acceleration, and this xx, yy, zz, these are normal stresses. The other things are tangential stresses. These are forces, and these are pressure forces, and these are body forces. And this entire equation is in the non-conservative form. This one, all these equations are non-conservative form. If I add the continuity equation on this left hand side, it will become the conservative form like this, and it can be written in the form of vectorial form like del dot rho u v bar, del dot rho v u v bar, del dot rho w v bar. So this is the equation. So this is about the momentum equation. So what we did here in today is, we have considered the Newton's second law of motion, mass into force, net force is equal to mass into acceleration. We consider the normal force, normal stresses, effects of normal stresses, effects of the tangential stresses, effect of the pressure forces, effect of the body forces, and we added and we got the net force equal to mass into acceleration. That is the momentum equation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.